Hi guys, welcome to Learn Electronics Repair. We've not done any ATX power supply repair for a little while, so let's have a look at one. This was amongst the PC finds I had at the weekend, last weekend, so this came from the flea market with a PC, and the motherboard in the PC was quite corroded. I then thought it would be worth trying this power supply. It is apparently rated as a 750 watt supply, but to be quite honest, it's quite small inside. I'm not quite sure if they're real watts or Chinese watts. The PFC is passive PFC, so this is quite an old power supply, but I thought it might be interesting. I opened this up on the previous video. I didn't test it or anything else. I just thought because of the corrosion on the motherboard, it was worth looking at the power supply before we just plug this in, even using a current limiter. So let's see what we have. And it looks like we have a problem down here. So we see two resistors, one caked with, well, what looks like fungus if you watch The Last of Us, yeah. But it's some sort of corrosion, and this might have come out of these two capacitors, or this may be the remnants of glue which was holding them in place. So the other resistor, I think you can see the colour code on it, which is black, green, yellow. So that's 150 kilo ohms, and probably the other one is the same value. These probably connect across the capacitors, one resistor across each, and are there to discharge the capacitors when you power down, to give it some sort of discharge path. We can look at the rest of the power supply. Let's see what we have. So we have maybe a little bit of a corroded area down here too. Yeah, on that resistor there, some in there. This area doesn't look so bad. Okay, doesn't look too bad, that area. This is the high voltage side. So these are the switching MOSFETs down here. The smaller one to the left there, that will be the standby supply. Then we have two, you can probably just see the second one, switching MOSFET down there. Those look okay. And this is the secondary side. So these are the output capacitors. Visibly they look okay. Doesn't mean they are, but it means they quite probably are with these sort of power supplies. And we can see a little bit more, so we can just look under here. This is the control chip for the switch mode power supply, the pulse width modulator basically, and it doesn't look too bad down under there. So let's get this board out. Let's have a look what's happening over here. Let's make some basic checks first to see if it's safe to power this up, and then let's try it. Here's the PCB. We can see the mess is down here. Let's have a look underneath. Well, that's perfectly clean. I think this is probably either come out of the capacitors or it's the glue that was under them, as I thought when it was in the casing. Now it's a bit more obvious. So we'll unsolder these two capacitors and then maybe get a better idea. This one, I think, if you look at it, can you see this one looks slightly domed? I can feel it as much as I can see it, which obviously you can't, but I can tell you this feels flat and this feels convex. You can feel it. Let's get these unsoldered. Okay, and now we can see, so the PCB is actually fairly clean. I think this is the glue. And in fact, now if I'm wiping at that, it's actually coming off the resistor, and I think we can even see the markings on the resistor. Let's see if we can clean some of this up with isopropyl alcohol. If not, I'll unsolder the resistors and then we'll try. Let's just try this and see if this works. Well, it's coming cleaner. I'll also try to scrape away a little bit of the, I think it is dried up glue. Okay. I'm not scraping so hard to scratch the PCB, I'm just cleaning it off. Maybe have to unsolder the resistors as well, just to do it properly. Okay, some scratching there. That probably wasn't the best technique to use. I'd probably better to use a wire brush. But it's come fairly clean, and this is a single-sided board. In retrospect though, I think I would have been better doing that differently. Let's remove these two resistors anyway. They are a bit corroded. We can check the value. I'm pretty confident they will be okay. But we might as well replace them. I mean, resistors are nothing really. And if I'm going to unsolder these to clean the last bit of the board, I may as well put new ones in. If we look on the other side, you'll see one resistor connects from here to here. So this is in parallel with this capacitor, and the other one is in parallel with the other capacitor. So that's exactly what these resistors are there for. They are to discharge the capacitors once the power is removed. Probably as a safety thing as anything else. What's this? Is this a little bit of solder or something? Well, I'm not quite sure, but I've got it off the board. It's probably from when I was desoldering. Yeah, it'll be from when I was desoldering these, basically. So I'll unsolder these anyway. We can just check the board again. This glue can become conductive, so it's best to remove all of it. Although, having said that, it doesn't usually cause a problem. These should be quite simple to unsolder. I'll use braid. Probably a bit of fresh solder as well, actually, is going to help. Obviously, you could use a desoldering gun or desoldering pump or something. I think this will do just fine. And then we can actually push on the end of the lead with the soldering iron tip. And it should just move up away from the board. Like so. Okay, so that should now be loose. Yeah, it looks like it is loose. Same with the other end. Adding fresh solder definitely helps a lot. Same trick again, so that's another good thing with this type of bit. You've got a nice strong flat end on it to lift these. Possibly with a fine tip you'll bend the tip of the soldering iron. Okay. I have, by the way guys, a C245 handle and tip for the Sugon soldering station. I have the 95 watt one that was ordered a few weeks ago from AliExpress. Should be here soon, so I've ordered the same style of tip for that one. Let's see if that works any better, notably than the T12. Be interesting. Okay, these should come out without any messing about. Yeah, it's just coming loosely, no force involved. That one too. This time I'll try a wire brush instead. Probably what I should have done before. Okay. Yeah, that was a much better idea, guys. Don't do what I did the first time. Just take that as a good demonstration of how not to do it, yeah. But when I start these videos, I never know exactly what's going to happen. Yeah. That's most of the fun of this channel, I think. You can see that came much cleaner without any additional scratching, so that proves the point. So these two capacitors and our power supply, I'll show you how they're connected and how the resistors are connected. We have AC coming in to 20 volts through some filters and such like, but the thing is basically it comes through a bridge rectifier, and this gives us a positive and negative output. The positive output connects to one of the capacitors. Okay, And then we have the other capacitor in series, and that goes to the negative. Also connected in here, I didn't draw it but I'll put it in, is that large choke that we see fastened to the side of the case. That is what's called a PFC circuit, passive PFC. It just means that the power supply puts a more stable load on the mains, if you like. It also helps to prevent the high frequency switching spikes from the power supply going back that way as well. But you also have filters down here to do the same thing, more inductors. So our power supply has then two output transistors, and they're connected like this. They're almost always bipolar transistors. In fact, I think probably much always bipolar transistors connected like so, and we have two of them. And these are connected to a controller, a pulse width modulator chip. 1, 2. It's more complicated than that because the pulse width modulator controller on this power supply is on the low voltage side, and it uses a transformer to send these signals. But this is the principle, so don't worry about that, okay? Don't go into the comments below about it, guys. Yeah, I know. And now I've told you guys, you know as well. So those are our two switching transistors. The transformer, well, that's connected here, and I'll use a different colour. So we have, from the junction of these two, the primary of the transformer. We then actually have another inductor, which in actual fact I will show you where it is, because you're thinking, well, there's the transformer. It's not these inductors. This other inductor is actually a winding on this one. This is the one that is driving the switching transistors that I mentioned as the way it actually works, okay? So the path is from the junction of the two transistors through the primary, through a winding on this one, and then it goes through a capacitor. That's that one. So from here, we have a connection across here to the capacitor I mentioned, the high voltage capacitor, and that goes to there. This is called an LLC circuit because there's two inductors and one capacitor. L, inductor, L, inductor, C, capacitor. This is what's called a resonance circuit, and you can go and look up how an LLC works. Hopefully when you look for that on YouTube, you'll find my video, because my video actually is the best one to explain how it works, yeah? So hopefully you'll click on that one. I would advise you to. So you can go, and I'll link it from this video, how the LLC works. But basically what it does is, these transistors are switched by this controller alternately. They don't switch on at the same time. So first it switches this one on, then it switches it off and switches this one on, switches off, switches this on again, and backwards and forwards. And what that does is it connects this point, the top end of the transformer primary, alternately between 320 volt and 0 volt. It's a switch. Each one's a switch. It switches to here, to there, to here, to there. And what that basically does is it puts a square wave 320 volts high on this end of the coil. Now the LLC is what's called a resonant circuit. It resonates at a certain frequency. The best way to describe this is, imagine, as I said on the other video, which you can go and watch, this is like a bell. And this square wave is the equivalent of you hitting that bell with a hammer. Bam, 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 bam. Now, if you've ever done this with the bell, you will know that no matter how fast you hit the bell, bam, 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 or you just go boom, 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 that bell will ring at a certain frequency, and it will ring at the same frequency no matter the speed at which you're hitting it. So what these pulses do basically is put energy into this circuit. This circuit, like the bell, rings, and that ringing is a sine wave. And the sine wave is exactly what the transformer wants to efficiently generate voltage into the secondaries. So that's how the circuit works. If you do want more details, you can look up the other video. Why does an ATX power supply have two bulk capacitors? And that's really why. Now our two resistors are connected like this. 220k, 220k, and they connect to here. So each one is across one of the capacitors. Now if you look on my video, of course, how does the LLC work, you'll see that the LLC doesn't require these resistors. They're not part of this resonance circuit. So the only reason I can think that of why these are here is quite literally so that when you power down, they discharge the capacitors. One of these resistors is open circuit on ours. I don't believe for 1 minute that would stop it working or affect the way it works, but I also think one of these capacitors might be open circuit, so let's test them. I have the capacitors here. These are 820 microfarad, 200 volts. Let's test them with the capacitance meter. Well, that one reads 300 and a bit, yeah. This one actually reads 300 and a bit, so they're both reading much lower than you would expect. Let's check the ESR as well. These are not specifically low ESR capacitors, but we can do this. So we'll connect our capacitor. They probably will read very low. Yeah, 0.06, it's rather low. .08, about the same. So if these capacitors are bad, they're both bad. You can see probably now, if I just hold it, you can see that this one is domed a little bit. Let's see if we've got any suitable ones we can put in place of these. Well guys, in fact I don't have. I have some 470 mic 200 volts, that's about the closest I have, in a larger value. They only read about 200 microfarads or so. They again are pulls, so they may just not be very good. So what I'm going to do is put these back in. I'm interested to see whether, if these are lower value than they should be, it prevents the power supply from running. I think if anything the power supply would run with the lower value capacitors, but maybe it would affect the performance at high power ratings towards its maximum power rating. But we can try. It's an interesting experiment to see if it works with these. Okay, I've changed the resistors while I was at it. Might as well. I've refitted the capacitors. Is there anything else we should check on this? Well, as soon as we're here, why not? I think we may as well at least check if there's any short circuits on the output transistors and if there's any short circuits on any of the low voltage outputs. If we look on the underside, I think you can see quite clearly one of the output transistors is here, 3 pins. The other one is here, 3 pins. And the smaller one is the standby supply. Let's see if there's any short circuits here. I'll switch to continuity mode. In fact, actually, I'll switch to diode mode. Okay. Right, let's see. So we have one transistor here. Here, I think this is base collector emitter. We can try. One bleep 500, that's a diode junction. That's another diode junction. So this is base collector, base emitter. And this is collector to emitter. With the positive, if you like, the red lead to the collector should read open, and it may read like a diode this way. Yeah, that's good. Next one, another NPN transistor. So base collector, diode junction, base emitter, diode junction. With the positive to the collector, it should read open. That's the way when it's normally powered up. And the reverse direction probably read like a diode. Okay. The reason it reads like a diode in reverse direction is just other circuitry. This is a MOSFET most likely. So that, yeah, reads open. Reads open. This will probably read open. No, it's climbing up. Yeah, it read open. This may probably read like a diode in reverse because it's a MOSFET. Effectively, you have a reverse biased parasitic diode in the MOSFET. So that reads okay. So I'm happy that there's no major shorts on the output of this. Another good place to check if we want to be sure is the bridge rectifier. These are the two AC. This is the positive, I think. Yeah, the chamfered edge is the positive. So test this one then. So to test this, if this is the positive output, black lead to the AC should read open. Okay. And the red lead to the AC should read like a diode off both of them. Diode. Diode. So that reads okay. The negative one reads the opposite. So the black lead to the AC should read like a diode. Like a diode. But the other way around should read open. Okay. And we wouldn't expect to find a short across the bridge rectifier either. And we don't. So all the high voltage side reads okay to me. Let's look at the outputs. This is quite easy. In fact, the easiest way is probably just to read on the ends of these cables. Okay. So ground, 12 volts. Probably read like a low value resistor here. Quite often there's a resistor. In fact, we'll go to resistance range. You expect to see like a resistor, maybe a few hundred ohms or something. Yeah, a few hundred ohms. There you go. Climbing up now. 5 volts reads open. 3.3 reads like a resistor. That's normal. So on the 3.3 volts output, you'll see we have a fairly low value. Is it 13 ohms? We'll just check again. Ground, 3.3 volts. And we read, yeah, 13 ohms. So this is a resistor from 3.3 volts to ground. It'll be on the board here somewhere. And this is to put a permanent load on the 3.3. The reason we do that, and it's almost certainly going to be, by the way, that resistor, which is 1 0 and no zeros, 10 ohm. Looks a little bit dirty actually. I don't think there's a problem with it. Let's get some focus on it. Actually, that looks like it might have a little burnt patch on it. I'm not sure, but I'm reading about 13 ohms. That's probably glue actually. So the reason we have this resistor 13 ohms on the 3.3, as I say, it puts a bit of load on the 3.3 volts rail. And the reason we do that is because the 3.3 volt rail is the one the power supply monitors. So it monitors the 3.3 and adjusts the pulse width modulation to keep that at 3.3. All the other voltages will be correct just due to the ratio of the number of turns in the transformer. It doesn't monitor the other ones, it only monitors the 3.3. So by putting a bit of a load on, let's say it was 12 ohms, 13 ohms on 3.3, Ohm's law will tell us that's about 250 milliamps of load. So it needs that to stabilize. If you didn't have a load, what would happen is the capacitors would charge up on the 3.3. Once you went above 3.3, the switch mode would try to reduce the drive to get less voltage out. It thinks I've got enough now, but there's nothing to discharge the capacitors, so they stay charged at 3.3, so it reduces the drive a bit more. And again, it stays at 3.3 because there's nothing to discharge the capacitors, but the other voltage rails will go down. Yeah, there's no way to stabilize the power supply unless there's some load. So when you reduce the drive, the voltage in the capacitors drops a little bit. That's why we have a load. The other thing you'll just notice, I have mentioned this before, but I'll mention it again. You'll see that on the orange wires, which is a 3.3, one of them has a brown wire. This is where the power supply is monitoring the 3.3. It's not monitoring it on here, it's monitoring it here. Why? Because there will be a voltage drop down the orange wires when the circuit board, the motherboard, is drawing power. Okay, and the more power the motherboard draws, the wire will have some resistance, so Ohm's law tells us the voltage here will go down. That's why it's using this brown wire to monitor the voltage here. The brown wire, no current is flowing in it, it's just a sense. So the resistance of the brown wire doesn't matter because there's no current flowing, it's all negligible, yeah? It's the resistance of the orange wires that affects the output voltage. So that is a very quick lesson on ATX power supplies again, yeah? I have the power supply plugged in, not switched on yet. It's connected to my current limiter. You can see well, it's there, yeah, the light bulb. So if I power this up now, what you would expect to happen is the current will run into these capacitors to charge them, basically. So the bulb should just come on bright, for instance, and then go dim or go off. Let's see what it actually does. Well, it does exactly what I thought it would do. So that tells me there's no shorts, at least on the input of this. It doesn't say, for example, if there's something wrong with the drive to the output transistors, it might not go pop when you power it up and start it up, but there's certainly no short circuits at the moment there. Let's connect our analyzer and then let's see what the power supply does. I've just rearranged it on the bench a little bit so we can actually see the display on the analyzer. We'll switch the current limiter off and we'll power it up again. And this is running. The reason it's bleeping at the moment is because I don't have the 4-way connector attached to it, basically. But it's telling us we have 5.1 volts on the 5, we have 3.3 stable, we have 12.3, 5.1. I mean, this is just running perfectly fine, yeah. It's usual to expect the minus 12 to be a little bit low, 11.6, that's quite normal. So our power supply is running. This is without a load, with those capacitors reading rather low. I think if I was going to use this for myself, or certainly if it was a power supply I would sell, obviously this is not the sort of thing you sell, it's old, it's an interesting tool to learn from. But if I was going to use this for myself, I would change those capacitors. Either find some poles that test correctly or just order a couple. So we have that one working. We can't say it was much of a repair, but I think we can say we learned some things today. Hope you enjoyed that. I will be doing more of all sorts of repair, including power supply repair, on upcoming videos, and I look forward to seeing you all soon on another Learning Electronics repair video. Ciao for now, guys.